So in the last module, we had just completed momentum equation. Let's see the slides. So we just applied the Reynolds transport theorem for the momentum equation and we applied sigma FCV. So we said that there are two forces, that is the surface forces and the body forces, and then we kept the left hand side we got it as rho du by dt, and we took the momentum, that is the forces acting in the x direction, we kept all the forces in the x direction. We got this Cauchy's equation and substituted for sigma xx, sigma xy, sigma xz in terms of velocity gradients, and we got these three equations, that is which we wrote this as here. So that is, this is the x momentum equation, this is the x momentum equation, this is the y momentum equation, and this is the z momentum equation. And remember, we had derived the continuity equation as d rho by dt plus rho of del dot v equal to 0. So total we have 4 equations and the 4 unknowns are u, v, w and p. Okay, so we have 4 equations, 4 unknowns. So mathematically it is well posed, but because of the non-linearity of these differential equations, we cannot have a general closed form solutions of these Navier-Stokes equations. But for some reduced forms, you can get the closed form solutions. So that's what we derived, and then we went to reductions of this and we removed the viscous forces and we derived the Bernoulli's equation from this. And just remember that this is g sine theta, this is rho g sine theta. Because of that sine theta, this is actually rho g sine theta, that sine theta is del z by del s. I just wanted to recollect that, and we got you the Bernoulli's equation. So in this module, what we are going to do is, now we are going to take up the conservation of energy. Okay, so let's take up the conservation of energy. So please tell your students that when you are deriving conservation of energy, the equations are going to be lengthy. They should be mentally prepared for writing large equations, I mean lengthy equations. You should keep their momentum with you. So that's about conservation of energy. Let's get started with this. So from first law of thermodynamics, we know that dE is equal to dQ plus dW. What is dE? That is the increment in energy. So what is the energy we are talking about? Kinetic energy plus thermal energy. Of whom? Of the system. And dQ is the heat transfer to the system. And dW is work done on the system. Here we are in the system mode. We are in system. Okay. Now I need to apply the Reynolds transport theorem for the energy equation, because this is the equation stated for the system. Reynolds transport theorem is the theorem which transforms the law from system to control volume. So what does that say? That is dB system upon dt is equal to dou by dou t of rho b dV of control volume plus rho b v dot n dA across the control surface. So what is B here? B is equal to E, which is equal to internal energy E plus kinetic energy U squared plus V squared by 2. And just to remind you, capital B is equal to mB. Capital B is equal to mB. So this equation on the right hand side would reduce to dou by dou t of rho E dV of control volume plus rho E V dot N dA is equal to whatever is happening on the system, that is dq plus dw will come for the control volume also, that is rate of heat transfer into control volume by conduction, because the heat transfer is going to take place by conduction, plus now work done. Who is doing the work? All the forces are doing the work, surface forces and the body forces. So rate of surface and body forces doing work on control volume. Just if you see the slide for a minute, if you just see the slide for a minute, so you get, this is the left hand side, that is dou by dou t rho e dx dy dz is, if you just go to the slide, so you have rate of increase of E in CV, that is the first term, and rho E V dot N dA is the rate at which E is entering through the surface of control volume and it is leaving through the surface of the control volume, and right hand side is the same. So back to right up. So if we start now, let us try to work out only the left hand side. Let's take up left hand side. Okay. So for this left hand side, so the first term is dou by dou t of CV rho E dV is equal to del of rho E by del T delta x delta y delta z. Is that right? Now you have the control volume parallelepiped we are going to write this in 2D, but although I am showing it in 3D, because 3D energy equation will become very lengthy, handling on the board would be very difficult. So I would strongly recommend you to limit yourself to 2D only, although we would write everything in the figures, everything in 3D. So we get a 3D feel, but we are writing for 2D. So you have what is, that is I am writing now rho E V dot N dA across the control surface. This term I am writing, that is what is entering, rho E V dot N is going to be U dy dz, that is this is delta x delta z, that is this is delta x delta y delta z, that is rho EU area is delta y delta z. Is that okay? Rho EU dot N dA. Minus plus we will come to that little later on. What is getting out is rho EU delta y delta z plus of del of rho EU upon del x delta x delta y delta z. That's about the x direction. Okay. So now you have the y direction, you have rho EV delta x delta z. What is getting out is rho EV delta x delta z plus of del by del y of rho EV delta y delta x delta z. Okay, that's it. As I said, I will write only two directions. So whatever is getting in, as I said already, negative, whatever is getting out is positive. So I don't think I should write all the terms and do it again. This is minus, this is plus. So this term is going to get cancelled out with this term. This term is going to get cancelled out with this term. So I am going to get this rho EV dot N dA is equal to, because these are pluses, so I will get del of rho EU upon del x plus del of rho EV upon del y into delta x delta y delta z, right? So you have LHS equal LHS upon delta x, delta y, delta z equal to del of rho E by del T plus del of rho EU by del x plus del of rho EV by del y. Okay. So now we will expand this. We will expand this and write it in some nice form. So to get that, we will have to just expand this, that is rho into del E by del T and plus E del rho by del T. So I kept one constant and the other I differentiated. This first term is over, plus I am going to keep here rho U and E separate. So what do I get? So I get rho U means rho I have taken common. So you get U del E by del x plus E I have taken away. So I get del rho U by del x. So the first term, second term is over, plus rho V. So that is V del E by del y plus E I have taken common. So I get del of rho V by del y. So these are the terms I get. So remember, this is nothing but by my continuity equation, I can equate this to 0, and whole of this is nothing but my total derivative of E. So that is, this is LHS upon delta x, delta y, delta z is equal to rho dE by dt. Recollect, E we wrote it as d by dt of E plus u squared plus v squared by 2. So let us keep this equation in our mind, that is LHS we are through. Let us take up the right hand side. What is there on the right hand side? Rate of heat transfer into CV by conduction. So let us take up that term first, that is rate of heat transfer into CV by conduction. Okay. So you get, let us draw the control volume. Delta x, delta y, delta z. So what is the heat transfer in the x direction? So you have qx dot delta y delta z. And what is it getting out? That is qx dot delta y delta z. You would have derived this, this will be familiar to the students because you would have derived this in heat diffusion equation derivation. So you can tend to go fast here. Del qx dot divided by del x, delta x, delta y, del z. In the y direction, you have qy dot delta x, delta z. And what is getting out is qy dot delta x, delta z plus del qy dot upon del y, delta y, delta x, delta z. Okay. So heat transfer into the system is positive, into this term would be positive, and heat transfer getting out of the system, or the control volume here in this case, control volume would be negative. So this term would get cancelled with this term. So I will be left out with here is equal to minus of del qx dot by del x in the x direction, that is delta x, delta y, delta z. Okay. And in the y direction, this would be positive and this would be negative. So you have this term getting cancelled out. So you have del qy dot upon del y plus del qy dot upon del y into delta x, delta y, delta z. So we just completed rate of heat transfer into CV by conduction. Now we have to take one by one force and see how is the rate of work done by each of the forces. So now let us take up rate of work done by pressure force, rate of work done by pressure forces. So you have parallelepiped again. So delta x, delta y, delta z. So you have pressure force which is acting, so that is P delta y delta z into rate of work done. Rate of work done is force into velocity. So this is the force P delta y delta z. Velocity in the x direction is u. So again which is acting in the other side is P delta y delta z into u plus del of up by del x delta x delta y delta z. So in the y direction you have P delta x delta z into v, and again on the top surface you get P delta x delta z into v, force into velocity, plus del of Vp by del y delta x delta z. Okay. Now what to take plus, what to take minus, this always students get confused. Here we need to go little slow. See, work rate, rate of work done, that is W dot equal to F into U cos theta. This is our, if you basic physics says so. So if you see here, pressure and velocity, that is force and the velocity are in the same direction. So theta is 0, theta is 0, so cos theta equal to 1, so that is plus, cos theta is 1, so it is positive. Now here you see pressure is acting inward, but the velocity is acting outward, correct? So your angle theta is 180, so cos 180 would be negative. So you have, that's why you have these terms positive and these terms as negative. So the first terms anyway get cancelled out. So the work, rate of work done by the pressure forces, we would be ending up with negative terms, because I have shown you why they are negative here. Okay. So you get that as minus of del up by del x plus del Vp by del y delta x delta y delta z. Remember, I am not writing again and cancelling it out, because it becomes too difficult when you are doing it on the board also. Just show them that this is going to be, this rate of work done would be positive on the control volume, and this is going to be negative work done on the control volume. So that way they will be able to understand this is positive and this would be negative. So that's how we have arrived at this. So this is the rate of work done by the pressure forces. Similarly, let us do the rate of work done by the normal forces. Okay, rate of work done by normal forces. Okay, so again same parallelepiped. Actually we can say that normal stresses in a jiffy we can write this, that is normal stresses are going to be opposite to that of pressure. So minus should become plus of what we got for the pressure, but still let us do for the sake of completion, so that the student does not get confused. We can come to that conclusion after doing again the same thing. So it's not repetition. So we are doing it, student is doing it for the first time, so it's worth doing once again. So you have now, this is sigma xx into delta y delta z into u. Notice I have taken the direction outward because sigma xx is in the outward direction. So, here you have sigma xx u delta y delta z plus del of u sigma xx upon del x delta x delta y delta z. Similarly, you have sigma yy delta x delta z into velocity. On the top surface you have sigma yy delta x delta z into v plus del of v sigma yy upon del y delta y delta x delta z. Again same fundamental idea we have. You see sigma xx is in this direction and u is in this direction. So, theta is 180. So, cos theta would be negative. So, this term would be negative. So, similarly here sigma xx is in this direction, u is in this direction, theta is 0. So, this term would be positive. Here sigma yy is actually outward, but the v is in this direction. This is sigma yy, v is in this direction. So, you have theta 180. So, this term would be negative. Here sigma yy and v are in the same direction. So, this term would be positive. This is where they get where to take negative, where to take positive, they get confused. This is how we can understand ourselves, so that they also understand that what to take negative and what to take positive. So, we get, what is that we get? So, we get that del of u sigma xx upon del x plus del of v sigma yy upon del y into delta x delta y delta z. Remember these terms, all first terms are getting cancelled out. So, you just see that it is the same. If you just put p equal to minus sigma xx and sigma yy, you are going to get the same equation. But just like that writing, the student may not understand. It is a good idea to rederive this once again. So, we have completed normal forces, normal stresses. So, now let us take up work done, rate of work done by shear stress, rate of work done by shear stress. Okay. So, here if I draw that, delta x, delta y, delta z. So, you have the shear stress acting in this direction. Okay. So, you have sigma yx delta x delta z. Here it would be sigma yx delta x delta z plus del of u sigma yx by del y delta y delta x delta z. You see here sigma yx is in this direction, but the velocity u is in this direction. So, here I missed out, sorry, this into u, velocity is in this direction. So, theta is 180. So, this is going to be negative. So, here sigma yx and u are in the same direction. So, this term would be positive. Okay. So, now there are two more stresses, that is sigma xy, you have this side, this is sigma xy velocity v into delta y delta z. Sigma xy is in this direction, but the velocity is in the bottom to top. So, it is in opposite. So, you are getting negative. Okay. So, here this would be sigma xy v delta y delta z plus del of sigma xy v upon del y, sorry, del x delta x, delta y, delta z. So, with the same logic what we used here, sigma xy and v are in the same direction, so whole of this is going to be positive. So, these first terms are going to be getting cancelled out. So, I am left out with del of v sigma xy upon del x plus del u sigma yx upon del y into delta x, delta y, delta z, delta z. So, if I combine all of this, all the works done so far, so I am going to get rho d by dt of E plus u squared plus v squared by 2 is equal to k del squared t by del x squared plus del squared t by del y squared minus of del of up by del x plus del of vp by del y plus del of u sigma xx by del x plus del v sigma yy by del y. I am just writing all the terms what we derived so far plus del of v sigma xy by del x plus del u sigma yx by del y. Remember, delta x, delta y, delta z is getting cancelled out, and I had not derived what is the rate of work done by the body force. So, it would be ufx plus vfy. Remember, fx, fy are the body forces in the x and y direction per unit volume, and I am also adding one more term, that is volumetric heat generation. Volumetric heat generation. If anything happens within the control volume, some heat is getting generated by whatever means it is, it can be accounted with by this q dot triple prime. So, we need to do this algebra and get the equation in the form of temperature. We have not still arrived. What is that we need to do? E has to be written in terms of temperature. Sigma xx, sigma yy, sigma xy, sigma yx have to be written in terms of viscosity and velocity gradients. Once we do all of that, we will get an equation in terms of temperatures and velocities and pressure. So, with this, we are going to stop this module and do the algebra of this equation and get this in terms of temperature in the next module.